Hello everyone, welcome to our video. In this video, we are going to do a numerical based on column base. So basically, we're going to do a design of column base. So we will do a numerical on that. In our previous video, we talked about column base. What are the different types of column base? What are the function of what are the function of column base? How does our slab base and how our gusset base transfer the load? What are the cleat angle column? How the load is transferred through our angle bolts, through our bolts, etc. We've already talked about the basics of our column base, types of our column base, and regarding basics regarding the theory regarding design of slab base. So do check out that video. In that video, I have explained the basics regarding whatever we are going to do in our video through numerical. So if you haven't checked that video, do check that video and do check this video. You can find the link to the playlist through our description box. So in this question, what we are going to do is first let's read our question. What we are going to do is we are going to design a slab base for a column ISHB 300 at the rate 577 Newton per meter, carrying an axial factor load of 1000 kilonewton. So you can see the word axial factor load. So you need to remember this word axial factor load of 1000 kilonewton. M20 concrete is used for foundation, provide a welded connection. So you can see this in this case where we're going to provide a welded connection. So we need to remember all these words clearly. Between column and base plate, use Fe 410 grade steel. So as you can see, basically we have got the value for our we have got the value of FCK, we have got the value of FCK as from here we have got the value of Fy as well, and next we have got the value of our load as well. And now firstly we need to find our dimension of column. So as you can see it is said design a slab base. So right now we are designing a slab base, not a gusset base. So we're going to designing a slab base for column ISHB 300 and then 500. So we can find different dimensions such as D, BF and TF. So for that we need to go into our handbook. So we need to go into our handbook. So if you move on, so right now we are designing a ISHB 300. So let me just search ISHB 300. ISHB 300 is over here. So you can see over here ISHB 300. So as you can see, you can find ISHB 300, but there are two ISHB 300. So which one are you going to choose? So we have our another value as well. We have our 577 Newton per meter. So but we have in weight per meter, which is in kg. So what you can do is you can basically multiply this value 300. Sorry, you can basically multiply this value 577, divide it by 9.81, or you can multiply this two value with 9.81 and you can find which one is the right one. So right now I'm not going to do that, but if you can multiply that and you can find out this my correct value. I think I don't remember exactly, but I think it's the 60. I think you get 63.0 when you multiply it. So what you're going to do is you're going to basically divide 577 577 divided by 9.81. So you can do that. So when you do in the calculator, let me check that out quickly. 500. So you have 577 divided by 9.81. It is equal to 58.81. Sorry, so this is the top one, 58.81. So we are going to take the depth of section, width of flange, and thickness of flange. So as you can see, what does H refer to, what does B refer to, and what does thickness of flange TF refer to. So we'll be taking all these we'll be taking the value for 58.8. What we have basically done is we have divided 577 newton per meter by 9.81 into converted to kg per meter. So we'll be taking this value of h as these three values. Firstly 300, 250 and 10.6. So we have taken the same value 300, 250 and 10.6, and we have written it as D, BF and TF. So this is my column. This is going to be my slab base which are designing, and this is my column base of M20 concrete, my RCC column base of M20 concrete, and this is my column of ISHB third, and it's basically transferring my 100 kilonewton force. It is transferring 100 kilonewton factor load. So as explained before, firstly we need to find the bearing strength for concrete. So in my video I'll be explaining each and every point with reference to our code book. So firstly we have our bearing strength for concrete. So my procedure one. So as explained before, my step one is going to be Step 1 is finding out the bearing strength of concrete, which is equal to 0.45 FCK, but at the code it says 0.6 FCK. So if you move on to my code, if you move on to 7.4.1, as you can see, the maximum bearing pressure should not exceed the bearing strength equal to 0.6 FCK, but to be on the safe side, we'll be utilizing the value as 0.45 FCK. 0.45 FCK, so we have our value of FCK equal to 20 Newton per mm square. 0.45 into 20, we get 9 Newton per mm square. So we have our factor load PU as 1000 kilonewton. If we were given working load, we need to multiply it by 1.5 in order to get the value of factor load. So for now, second step, as you can see, in our second step, we are going to find the area of base plate. So we're going to divide PU divided by 0.45 FCK. So we have our PU divided by bearing stress. Bearing stress is equal to 9 Newton per mm square. So our PU is 1000. So this is in Newton, this is in kilonewton. So in order to convert it into Newton, we'll be multiplying it by 1000. So 1000 into 10 to the power 3 divided by 9, we get it as 111 triple. So that is 1 tens 100,000. So it's 11,111 millimeter square. So this is my top view or top view as well. So let me not. So let's move on to it for a little bit later. So now we need to assume equal projections of A from sides of column. So as I explained before as well, we need to keep the base of plate. Select the size of base for economy as far as possible. Keep the position on all sides equal. So as explained on my previous video, we need to keep the projections, both these projection in the x direction and y direction as same. So this projection or this spacing needs to be equal, this A and B. So as you can see, I have taken it as A and A. So this is my different figure. So now in order to, so I have assumed equal position of A from sides of the column. So we have found out my area. So basically my area is going to be L into B. So let me just explain you how this is done. You can just draw the figure over here. So this is going to be my slab base. So from my top view, this is my column. This is my steel column from the top base, and this is going to be my projection A, and this is my another projection A. This is up to here only. Okay, this is up to here only. This is my A. So now I have my this as 300. This distance is going to be equal to 300. So how distance is 300? So as you can see, I have told you, see this figure before. So basically I am seeing it from top, so I'm going to see it this way. So this is my H, and this is this value of H is going to be equal to 300. So this value is going to be equal to how much? 300 in this way. Similarly, other values, this most value is going to be equal to 10.6. This is my TF. TF is going to be, as you can see, this is my TF. This thickness of flange, and this is equal to 10.6. This is equal to 10.6. And finally, I have my width of the flange. I think BF is my width of the flange, which is 250. So this is my width, which is equivalent to 250. So my length, this is my length of the base plate. So I'm taking this as L. So what is going to be the length? So this is my A. So my length is going to be equal to 300 plus 2A. As you can see, 300 plus 2A. So my length is from this edge to this edge. So the middle distance is 300 up to here, up to this plate, while this remaining equal portion is A, and I have going to have another A over here as well. It's going to be 2A. So 300 plus A plus A is 300 plus 2A. Now let's move on to my breadth. So this is going to be my breadth 250. Again, upward portion is A, again downward portion is going to be equal to A. So 250 plus A plus A. Okay, again 250 plus 2A. So as you can see from this figure as well, I have 250 A, again downwards A, 250 plus A, 300 plus AA. So L is going to be equal to 300 plus 2A, and B is going to be equal to 250 plus 2A. So basically on solving this, we are going to value of our equal projections on all sides of the column, which is going to be A equals to 29.63 mm. So we're going to take this as 300 mm. So now we have our length of base plate. So length of our base plate is going to be 300 plus 2A, which is going to be 300 plus 2 into 30, which is 360 mm. Below the base plate is 250 plus 2a, 250 plus 2 into 30, 310 mm. So now our area provided. So our area required is this 11161 mm square, while our area provided is going to be length into breadth 260 into 200, which is going to be 111600. So as you can see, this value is definitely greater than our area required. So our area provided is greater, must be greater than our area required. So now moving on to our intensity of pressure W. So as you can see, after finding out our area, we have found our length and breadth. Next we found our size of the, next we found out the projections as well. Finally we need to find out thickness of plate. So we need to utilizing this formula, and we need to find out the, first we need to find out our intensity of pressure. So what does intensity of pressure refer to? So moving downwards now, we are going to find out our intensity of pressure W, which is going to be equal to Pu by A. Pu is again 1000 into the power 3 divided by A is this area provided, not the area required, but the area we are providing. So basically intensity of pressure refers to, so this is my column, we have our load P, this is going to be my base plate, this is going to be my column base. So intensity of pressure at the base basically refers to the load being when the load is being transferred to the base plate, a certain reaction force is going to be provided by my column base in order to maintain in equilibrium. So this reaction force, which doesn't allow the base plate to go inside the foundation or cause the failure of the structure or the rupture of the base plate. Such reactive force is known as our intensity of pressure, which is denoted by W, which is going to be equal to Pu. So this has the intensity as the as you can see our this reaction pressure. So simply let's say reaction pressure is acting at the base plate, so we need to divide it by our area of our base plate, which is A, which is going to be equivalent, which is going to be equal to 111600. So our intensity of pressure at the base W equals to 8.96 Newton per mm square. So we have our resistance value A equals to B equals to 10 mm. So basically we'll be utilizing this formula in order to find out our thickness of base plate. So again, if we move on to our code, we can find in 7.4.3.1 in page number 47, we have your formula for thickness of base plate. You don't need to remember any formula, which is equal to 2.5 W A square minus 0.3 B square gamma m naught divided by F R naught. So gamma m naught is going to be equal to 1.1. We can find this table from page number 30, table number 5. So you have a value of W, A and B respectively. So put on this value and we get the value of the thickness of base plate as 7.8 mm. But as you can see, as we have mentioned over here, your thickness of base plate must be greater than thickness of flange of compression member. So we have our value of thickness of flange of compression member as 10.6 mm, but we found the value of thickness of base plate as 7.8 mm. So 7.8 mm is less than 10.6 mm. So our criteria is TS, thickness of base plate, must be greater than or at least equal to thickness of our compression, the thickness of the base of it must be equal to the, it must be equal to our thickness of flange of compression member. But in this case it is not equal, so we'll be taking our value of thickness of base plate as equal to is equal to thickness of our flange, so it's going to be 10.6 mm. But let's say if we had the value of our TS as, let's say, 12 mm, but we had our value of TF as again 10.6 mm. In this case, we'll be taking our value of TS as 12 mm only, because TS is greater than TF. We'll be taking the value of TS equal to TF only in that case when the value of TS is less than TF. So we'll add up thickness of base plate as 12 mm. So as explained before, we'll be using 4 bolts of 20 mm diameter, 300 mm long to anchor the plate. So I will explain about the connections, just like our standard. So we'll basically using this only 420 mm diameter and 300 mm long anchor bolts. So now moving on to our welding part. So basically what are the size of the weld, and basically what are the different criteria regarding to the weld. You can see my video related to welding before seeing this part, but if you have already seen the welding, let's move on to our part. So in moving our welding, we'll be taking our size of weld as 6 mm. So we're going to directly take this as a 6 mm. You can perform calculations as well based on your, as we did on the problems of our welding, but this time we're going to directly assume. So our throat thickness TT is going to be equal to K, yes, it is going to be equal to Ks. So so as we know from our welding, as we've seen in our table, we're going to take the value of key as 0.7. So yes is 6. It's going to be 4.2 mm. 4.2 mm. So we have our value of throat thickness equals to k as, and for 60 to 90 degree, we take our value of k as 0.7. So since in our question nothing has been mentioned regarding welding, so we'll be basically taking the value of k as 0.7. So into yes, it's as 4.2. So now the design strength of filled weld FWT is equal to Fu divided by root 3 gamma MW. This is going to be equal to 410. This is given a question divided by root 3 into gamma MW 1.25. So again the value of gamma MW, gamma M0, all these values, values will be find out from table 5, page number 30 of our code book. So let's cancel it. Let's show you quickly. Uh, Page number 17. Page number 31, page number 30. So as you can see, you have the value of gamma m0, gamma m1 1.25 from here. You have the value of gamma m0 as well. So now we need to find out our required length of the weld. So firstly, let me find, in order to find out our required length of the weld, we will be equating it with our load. So Pu equals to LWTT into FWT. So we have my value of Pu as 1000 into the power 3, LW into TT is 4.2 into FWT, design strength of fluid is equal to 189.37. So I got my required length of weld as 1257 mm. So my required length of the weld. So this much amount of weld needs to be done in order to weld this structure together. So now we have available length for welding. So in order to find out our available length for welding, we have done. So let me show you at which part we are going to do the welding. So I have drawn the figure already. So we'll be doing welding in this part 1, 2. So this is, so as you can see this part, so as you can see the length of this part is 250. So as I explained before, so this equal to 250. So 250, draw the figure one more time in order to explain. So now regarding the welding, we need to learn in which areas we are going to perform our welding, so that we can calculate our this part, which is our available length for welding. So let me draw the figure one more time. This is going to be my base plate, slab base. This is my steel column. As you can see, this distance is equal to 250, while this distance is equal to 300. So I'll be performing, let me use red color to show my welding. I'll be performing welding in these two parts. Firstly, 1, 2. So we got my available length for welding as 250 into 2. So next we'll be performing welding in these areas. So as you can see, in order to find out the value for this area, so as you can see, this value is equal to 7.6. So as you can see, my this thickness is equal to 7.6. So firstly, let me write it over this way with black color. So this thickness is equal to 7.6. So now what we'll be doing is, I'll be doing welding in this part as well, this part, this part, this part, and this part. So now what we're going to do is, we're going to do 250 minus 7.6. So this total is 250 minus 7.6. I get this two part, but this two part is on this other side as well. So 1, 2, 3, 4. So for 4 parts, total is 250. Total is 250. I subtract this much part minus 7.6. I get 1 and 2. 250 minus 7.6 is equivalent to this two part, but these two part are in my right side as well. So 250 minus 7.6 into 2 into 2. So hopefully you have understood this part as well. This part as well. So 250 minus 7.6 into 2, and finally, okay, let me draw my figure one more time. What I can explain from this figure as well for my last part. What is the last part? 250 300 minus 2 into 300 minus 2 into 300 minus 2 into 300 minus 2 minus into 2. So into 2 is missing over. It is into 2 into 2. So let me draw my figure again. So 300 minus 2 into 10.6. What is 300? So 300 is this part, and again 2. Okay, let me explain from this part. So the reason where welding were to be done was this part and this part. We have already done set 150 minus 2, and another part was this part and this part and this part and this part. Next we'll be doing welding over this area as well. So this is my available length for welding. This is my another major area as well, which is going to be calculated by 300 minus 2 into 10.6. 300 300 minus 2 into, so this is my 300. If I subtract 10.6, one 10.6 and one 10.6 from this side, I get the first edge. So 300 minus 2 into 10.6, I get this, and there is another structure beneath this as well, which is also equivalent to total 300 minus 1 10.6, another 10.6. 300 minus 2 into 10.6 into 2. So I get a total available length for welding as 154 100 1542.5 mm. So let me explain this again. This is my structure. So you can skip this part if you understood the welding. So this is my first part. This is my first part. So we got 250 into 2. Again 250 minus 7.6. So this is my width 7.6. So basically I'm finding this part 1, 2, 3, 4. 250 minus 7.6. 250 minus 7.6. I get 1, 2. Multiply it with 2. I get this 2 part. And finally 300. 300 means this part 300 minus 10.6 is this part. 2 into 10.6, I get this part. Multiply it by 2, I get up and down part. So total, so this is my total available length for welding, and I find this as equal to 1542.4 mm. So now finally moving into my last part, I have effective length available for welding. Effective length available for welding is obtained after deducting in return at the rate of twice the size of the weld. So now in order to find out our available effective length, what I need to do is available length for welding L minus 2s into n return. So L minus 2s into n return, my L is available length for welding. So available length for welding is 1542.4 mm minus in return. So for our column, for our ISHB column, it's basically going to be equal to 12. You can remember that, but I'll explain how it is 12 minus 2 into s. So s is our weld, which is 6 mm. So how it is 12? So let me explain this from our figure as well. So this time let me use purple color. So as you can see, our end return is basically the extra part of the welding, the extra end which we have. So I have explained that in my welding video as well, but let me explain you quickly over here. My one end return is over here, 1. Next end return is over here, 2. Next is 3, 4, 5 and 6. Again 7, 8, 9, 10, 11, 12. As you can see, and are my extra part list. In simple mode is the extra part where I'm been doing the where I'll continue my welding. So as you can see, I have shown this in my figure over here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I think I missed one part here. 12. This is my 12. So you can simply remember this value. If we put 12 into 2 into 6, we get my available effective length as 1398.44 mm, which is greater than my required minimum length 1257 mm for welding. So the first 6 mm weld is adequate, and this is my design related to my welding as well. So hopefully we have understood how the design of column base is done. So if you have any queries, you can comment down below, and if you liked our video, do share the video with your friends, do like the video, and do subscribe to our channel. And if you want to do any sort of help to our channel, you can help us through our pinned comment. Thank you.